Hello, today we're going to be covering Unit 1, Chapter 3, Chemical Bonds. Our first topic in that section is chemical bonds. So what are the main types of bonds? So the main types of bonds here are our ionic bonds, which have sole custody, our covalent bonds, which have joint custody, and lastly, our metallic bonds, which have communal custody. So let's talk about ionic bonds. So these are the electrostatic forces. When metals lose electrons, E minus, we call them cations. And when nonmetals gain electrons, we call that E plus anions. So when ions bond, they don't overlap in an ionic bond. So for example, here we have right here these electrons, so that electron right there. Why did that not show up? 1 second. So that, why is it not working? I'm so sorry. Okay, so give up on that. We have our one electron here and another electron here, but notice that these electrons are not touching whatsoever. And so that is why we have an ionic bond. So when we have ionic compounds, we have salts, solids at room temperature, ionic compounds that are normally called lattices. And a covalent bond is a form between nonmetals and nonmetals. So ionic is between metals and nonmetals, whereas covalent is between nonmetals and nonmetals. Covalent bonds share electrons, as we can see here, right here. They share those electrons. And when two atoms bound together covalently, they overlap, like we see in that image. So covalent compounds are called molecules, and they are independent. And most bonds are part ionic and part covalent. So let's answer some questions now. Let's determine whether CuCl2 is a ionic or covalent compound. Well, we know that Cu is a metal, so we can go ahead, Control C that, and put that in as a metal. Then we know that chlorine is a nonmetal, so we can go ahead and put that in as a nonmetal. So if we have a metal and we have a nonmetal, we know we have an ionic bond. So CuCl2 is a ionic bond. Let's determine whether or not NO2 is an ionic or covalent bond. So N, nitrogen, is a nonmetal. Oxygen, O, is a nonmetal. And when we have a nonmetal and a nonmetal, we get a covalent bond, like so. All right, let's move on to compounds. So molecular elements, so some nonmetal elements exist as molecules, diatomic and polyatomic. Oxygen, as a molecular element, is diatomic. And hydrogen is also a diatomic element. Let's talk about formula units. So formula units have some bonding patterns, have no set starting and stopping, also known as lattice. So this is ionic and network covalent. And whole number ratio of atoms are electrically neutral. So polyatomic ions are ions made up of two or more covalently bonded atoms. Hydrogen 3O plus is a hydronium ion. Some more examples of this include ammonium ion, hydroxide ion, nitrate ion, nitrite ion, acetate ion, sulfite ion, carbonate ion, and phosphate ion. Now let's talk about hydrates. So some lattice structures have extra room and water, and this will get stuck in the structure. And a hydrate compound that has been dehydrated is called an anhydrate. And that's what I have here, but let's go ahead and let's talk a little bit about um, how to find combustion analysis, because this is it's a pretty difficult topic. So we have our question here. A 1.5 gram sample of hydrocarbon undergoes complete combustion to produce 4.4 grams of carbon dioxide just carbon dioxide, and 2.7 grams of water. What is the empirical formula of this compound? So let's go ahead and solve this question. The first thing we want to do is we want to figure out how many moles of carbon there are. So we take our 4.4 grams, 40 grams, and we multiply that over 1, and we multiply that by 1 mole of carbon dioxide over 44.01 grams of carbon dioxide. Then we're going to multiply that by 1 mole of carbon. Notice how it's carbon and not carbon dioxide. And 1 mole of carbon dioxide. And when we divide 4.40 by 44.01, let me back up a step here. Now we're going to cancel out stuff. So we can cancel out our mole of carbon dioxide. We can cancel out our grams of carbon dioxide. So we're left with mole of carbon. So that's how we know when we divide, we should get a mole of carbon dioxide, which in this case would be 1.009 moles of carbon. So now we're going to take that mole of carbon that we just found, 0.1009 moles of carbon, and we're going to multiply that by 12.01 grams of carbon over 1 mole of carbon. And we get rid of the moles of carbon, so we're left with grams of carbon. So now we know we have 1.2116 grams of carbon. Great, we found our carbon, but now we have to go find our hydrogen. So we're going to go ahead and scroll down a little bit. Zoom back up. Okay, let's find our hydrogen. So we have 2.70 grams of H2O over 1. Make sure that's a 0. And we're going to multiply that by 1 mole of water over 18.02 grams of water. And now we're going to multiply that by 2 moles of hydrogen over 1 mole of water. So let's start eliminating. We can get rid of our grams of water, and we can get rid of our moles of water. So we're left with mole of hydrogen. So when we go ahead and multiply 2.70 times 2, divide that by 18.02, we are going to get 0.3000 moles of hydrogen. Now we're going to go ahead and take those moles. So 0.3000 moles of hydrogen. And we are going to put that over 1, and we're going to multiply by 1.008 grams of hydrogen over 1 mole of hydrogen. And we get 0.3021 grams of hydrogen. Now here we just got rid of our moles of hydrogen. So now we are going to do this. So our sample size was 1.50 grams. Sorry, that was messy. We're going to subtract the 1.2116 grams of carbon from that. And we're going to also subtract our 0.3021 grams. Oh my god, grams. What did I do? Okay. Grams of hydrogen from that. And we are going to get 0. 0.0 grams. This tells us that there is absolutely no room for oxygen in this sample. So we know our sample is made up of only carbon and hydrogen. So let's see how much of each we have. So we're going to take, we had 0.1009 moles of carbon. Oh, my bad. And we had 0.3000 moles of hydrogen. Now, when we look at these two numbers, we can tell which one's smaller, our moles of carbon. So we're going to divide everything by the moles of carbon. So we're going to get rid of our moles of carbon. Or we're not going to get rid of them. We're still going to have 1 left. Sorry, let me just erase that. So we're left with just 1 mole of carbon. And when we divide this by 0.1009, you're going to get 2.97, which we are going to round up to 3 because you can't have a part of a molecule. So, what am I doing? This is not going to cooperate with me. Okay. So now that we have figured that out, we can go ahead and see that we have 1 mole of carbon and we have 3 moles of hydrogen in our sample. So let's put this into a formula. So we can have C1H3, which tells us that there's 1 molecule of carbon and 3 molecules of hydrogen, or we can just write 3H3 because the 1 is unnecessary. If there was no carbon, like there's no oxygen, we wouldn't even include it. And lastly, I just want to go over, where is it? Let's go over precision versus accuracy. Zoom in on this pretty nicely. Okay, so here we have precision versus accuracy. So precision, let's start with precision. Let's start with accuracy actually. So accuracy equals, it's how close you are. I did not spell how right. Oh my lord. I'm so sorry. Okay, so how close you are to the actual value. So please don't mind my handwriting, but I talked you through it. So here on our chart, we can see, or our little diagram, we can see that accuracy, the points aren't spread close to each other, the red points, they're not spread close to each other, but they are extremely close to our value that we want, which is inside that black circle. And now let's talk about precision. So precision is how close the values are to each other. How close are to each other. Sorry, my handwriting was a mess. But here we can see that the points are really close together. However, they are a great distance away from the actual point. Okay, let's slide to the left and let's try practice problem. So we have our colors shown and we are going to be trying to figure out what is it. So start with pink. Is our pink one precise or accurate? Well, we can see that these points are not close to one another, so we can get rid of precision. And they're not very close to the actual value either. We have one pink right in the center, and we have one in the circle next to it, but our rest are just kind of floating around everywhere. So we have neither. Let's try blue. So our blue points are very close to each other, right here, but they are also very close to the actual value. So this makes it both. Let's look at our green. Our green points are very close to one another, but they are a great distance from the actual center, the actual value. So this makes it precise. Our purple points are not only very close to each other, but they are also very close to our actual value. This makes them both. Oh, oops, 1 second. Let me get rid of my drawing and then write both. And lastly, we have yellow. And our yellow points are very close to the center, but they are not close together like we have in our green, our blue, and our purple. So this makes them accurate. And that's all we have for today.